Continuing with discussion on sequence impedances and sequence networks of a power system component, in this session we'll discuss the sequence impedances and networks for transformer. A transformer in a power system is a three-phase circuit. It may consist of three individual single-phase units, or it may be a three-phase transformer. Although in the case of the transformer, the zero sequence series impedance of a three-phase units may be differ slightly from the positive and negative sequence values. Usually, to assume that the series impedance of all the sequence are equal regardless of the type of the transformer. That is, in the case of the transformer, we are considering the positive sequence impedance is equal to negative sequence impedance is equal to zero sequence impedance, that is equal to impedance of the leakage impedance of the transformer. That is, in the one of the statement, or it is a literature, the literature that to the power system, the elements of power system by Stevenson is noted that the reactance and impedance are almost equal for the transformer of 1000 kVA or larger value. That is, for 1000 kVA and larger value, the impedance and the reactance of all the sequence is equal, because the resistance is very small. And one more assumption we are making here, for simplicity, in all our calculations we shall omit shunt admittance, which accounts for the exciting current. That is, whatever you are taking consideration for I naught, that is R naught and X naught, they are omitted. Therefore, you are purely considering only the reactance of the leakage reactance of the transformer for representation. Therefore, the transformer are simply represented as their positive and negative sequence impedances in the positive and negative sequence networks respectively. That is, in the case of the transformer, it is a static device and it is a passive device, and in the positive and negative sequence it is represented by only its the reactance, that is a positive sequence and negative sequence. However, there is a representation in the zero sequence network can be more complex in the case of the transformer, because it is depending upon the type of the transformer connection. The transformer will be connected, that is, if you are using three single transformer for three-phase use, in that case those transformers can be connected, or even the three-phase transformer, they may be connected in star star, star delta, delta star, or star grounded, without grounded, all these things. Then the zero sequence path is depending upon the grounding of the transformer. Therefore, for the different type of the connection of the transformer, the zero sequence will differ. However, in the positive and negative sequence, it is represented by its respective positive and negative sequence reactance. First, we look into the sequence network of the transformer for in the positive and negative sequence network. I told you that is in the positive and negative sequence network of the transformer is represented by its positive and negative sequence reactances, and as such there is no voltage the source in the case of the positive sequence of the transformer, because it is the passive device. Therefore, the positive sequence series impedance of the transformer equal to leakage impedance, since the transformer is a static device. The leakage reactance does not change with the alternation of a phase sequence of balanced applied voltage. Even though if there is a transpose of the line in the case of the transmission line, it does not affect, it remains the same. And the transformer negative sequence impedance is also therefore equal to leakage reactance. Thus, for a transformer, it is very important, the statement that is Z1 is equal to Z2 is equal to Z leakage. Both positive and negative sequence reactances are equal to its leakage impedance. Now we are considering the resistance is neglected, that is nothing but leakage reactance. Therefore, in the network diagram, it is represented by Z1, that is Z1 is the the positive sequence, the impedance of the transformer. The current which is flowing in the positive sequence is IA1 and the terminal voltage is it is a VA1. It is not VA2. It is in the positive sequence. It is VA1. VA1 is equal to, it is the current which is driving here is IA2 and it is a reference. Similarly, in the negative sequence network, we have got, it is represented by Z2 and the terminal voltage is VA2 and the driving current in the negative sequence diagram is IA2. This is how we have to represent the positive and negative sequence diagram for the transformer. Here it is a VA1. It is a VA1. That is, I will make it correction here itself. That is, this voltage is it is VA1 and the current which is flowing here is VA2. Okay, fine. Now we'll move to the zero sequence network, which is a little bit complicated. That is, we'll start with the different configuration of zero sequence networks here. Zero sequence equivalent circuit of a three-phase transformer banks, that is, I'll make it in the form of a table. Just first I'll consider here the symbol of the, how we are representing the different configuration of the connection in the primary and secondary of the transformer in the symbol, and the what should be the actual connection diagram in the three-phase connection, that is in the second. And the third one is how we are representing zero sequence network per phase basis. These are the three things I am categorizing here. The symbol, how we are representing in the single line diagram, how exactly it is a connection diagram in the three-phase circuit, and how it is represented in the per phase basis. To start with, I'll start with the star grounded, that is, it is a three-phase transformer that is between P and Q. There are 2 points on the network, that is P and Q. In the between P and Q, we have got a transformer. That is, a primary side is star connected and grounded. The secondary side is star connected, and it can be represented by a three-phase circuit, that is, it is a star connected transformer with zero sequence impedance Z0, 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 and the primary is grounded, therefore it is the primary is grounded here. And however, the secondary is star connected and it is ungrounded, that is shown. Then the whole three-phase transformer is represented by either referred to the primary side or a secondary side. The total impedance remains the same, whether you can refer to the primary side or a secondary side, that was studied in the per unit quantities. That is, if you are referring the transformer impedance or reactance refer to any one side, it is remains the same. Therefore, then we have to look into the path for the zero sequence current. I told you in the while explaining the zero sequence network, the zero sequence current will flow only there is a ground is, that is, earthing is made. Otherwise, there is no path for the zero sequence current. Therefore, in this case, you can look into here. Suppose the zero sequence current there, if you are flowing from the P, that is a P2, you want to whether it is passing through the Q or not. Suppose the zero sequence current are flowing here, then there is a path here. But however, from here onwards there is no path here. There is here onwards there is no path. Just I will show you with the direction of the ink here. Just you can look into here. Suppose the current is entering into one of the phase here. If it's a current is entering here and the current is flowing in the ground here. But from here there is no entry to the secondary side, because it is this particular secondary side is not grounded. Therefore, there is a break here. Therefore, in the diagram, that is what we are showing here as okay. Now you can see the diagram here. That is from P, that is a P, that is the current is flowing here. Then your per phase basis were Z0. Therefore, I am showing here P and a Z0 here. Then once it is enter here, then there is no path. Therefore, it is shown as a gap here. That is, there is no flow of zero sequence current from P to Q because you have to show the gap because the secondary is not grounded. This is how we have to analyze for the star grounded and star ungrounded. Then we'll move to the next one, next combination. That is, we can to go to the next combination. That is, both the primary and secondary, they are grounded. Both secondary and primary are grounded here. Can look into here, that is, it's a star connected, it is also star connected. Therefore, what I am doing here is I am drawing here the connection diagram. Both the primary and secondary, they are star connected and grounded. Just you have to observe here the path for a zero sequence current. That is, the zero sequence current which is flowing from here. You can see here the current they are entering into here. Then there is a path for the zero sequence current here. Then it is entering into the ground and they are entering into the secondary winding and it will pass to the secondary winding, that is to the line, to the Q. There is a complete path for the zero sequence current. If you are taking only one phase, I am considering here the R phase. Similarly, it is meant for all other phases also. You can see here the current is flowing here, then they are entering into the neutral point and it is goes to the ground, then it is enter into the secondary winding and it is flowing. There is a complete path for the zero sequence current in the case of the star connected and it is grounded. Therefore, in the network, what I shown here is between P and Q, there is Z0, because I told you either this Z0 you can consider or this Z0. That is equivalent impedance referred to the either a primary and secondary. It is, I am simply representing by Z0. Either it is referred to the primary or it is a secondary. Therefore, what I mean is for a complete path is there for a zero sequence path. Therefore, it is represented here between P and the Q. In the next case, next combination, we have star connected primary with a grounded and the secondary is the delta connected. Secondary is delta connected and its connection diagram is shown here. It is star connected. The primary is star connected here. The primary is star connected and it is a grounded here and the secondary is a delta connected. Then we have to look into what is the path for the zero sequence current. That is, the current, it is grounded, the primary is grounded. Suppose the current is entering here. I am explaining only for R phase. It is similar to the B and C also. Starting from the P to Q, what I want is whether the zero sequence current will pass from P to Q. What is the path for that? How we are representing between P and Q? That is our objective. That is, you have to draw the zero sequence current diagram for this type of connection of the transformer. If you look into here, from P to, there is a entry into the current into the neutral and it is a grounded, the current is flow, then it is enter into the secondary winding of the transformer. Then the zero sequence current, they are circulating inside the delta. They are not flowing the lines of the secondary winding because it does not have any return path for the secondary. Therefore, the currents are circulating inside the delta. Means whatever there is a current which is entering here, that is goes to the ground. That is, it is circulating inside the winding itself. That can be represented here. See here. That is from P to, there is a current is flowing here. That is shown. That is P to here Q. That's sorry, P to the impedance Z0, and it is goes to the ground only. That is, it is circulating inside the delta. Therefore, it is B to Z0 and it is connected to ground. That is, if it is a grounded and it is a delta connected, there is no complete path for P to Q, because it is a delta connected in the line. In the line there is no flow of current here, but only they are circulating here. Therefore current is circulating here itself per phase basis. They are circulating here only. Therefore you have to show the gap in the between P and Q at this particular point. This is how you have to represent the zero sequence network for it is star delta. Then we'll see the second combination here, that is star and delta. It is not grounded here. It is secondary is delta. If it is not grounded, there is no existence of zero sequence current itself in this network. That how we are representing, that we'll see here. That is star connected, it is not grounded, because there is no entry of the zero sequence current from the primary to secondary, because it is not grounded at all. Therefore, how we are representing, just you have to look into here. That is, from P to here, there is no ground here, it is not grounded, it is end at this point only. It is end at this point only. Therefore, it is P to Z0, that is P to Z0, and there is a complete break here. Means there is no current is flowing. Therefore, if there is no current is flowing in the secondary, there is no existence of whatever there is a circulation here. In the previous case, it is a current is entered here, that is entered into the delta connected, that is circulated here. But first of all, the current is not there, which is flowing to the secondary winding, because it is not grounded. It is not grounded, there is no existence of a current. Therefore, you have to show break itself here, so that there is no current is here. Therefore, it is simply represented by Z0 and the break. There is no, this link is there. This link is there only when it is grounded. Only when it is the grounded here. Okay. This is for the star delta. That is, the star is ungrounded. Then we'll have delta delta connection. We have got a delta delta connection. In this case, whatever there is a current which is entering into the delta connection, the currents they are circulating inside the delta. That I will show you here in this diagram. That is what I am mean here is the current is entering into here, but there is no return path. It is offering very high the impedance for the return path. Therefore, you have to show the break. There is a current is circulating inside the delta. Here also in the primary as well as in the secondary, the zero sequence current they are circulating the inside. Therefore, in the network diagram, how you have to show, there is no return path, means there should be a break towards the primary as well as towards the secondary. We have to show as a break here. You have to show the break. Then the zero sequence current which are flowing inside the delta, that is represented with this Z0. This is Z0. This is how you have to represent the sequence networks for the positive, negative and zero sequence network of the transformer. In the next session, we'll see that how these connections are you have to realize with a switch diagram, that we'll see in the next session.